Okay, so um, welcome to the online version of our classroom. Hopefully, everybody can see me and can hear me and all of that. I am hoping that we'll be able to complete the rest of the class this way. Some things are not going to change, some things are going to change kind of drastically. In particular, homework is probably going to be mostly about the same stuff. We're going to be doing mostly online things. We'll probably do all online homeworks for the rest of the semester just because paper is kind of impractical right now. Um, otherwise, so lectures, basically the way class is going to be structured is we're going to spend about an hour of class each day from 8 a.m. to 9 a.m. Here in Discord. I will deliver content via lecture, which means that primarily um, that's not going to change particularly much. I could write on my tablet as if it was a whiteboard, and you can see that. So hopefully that will work out okay for delivering content. Um, then on top of that, for interactivity, that's the part that I'm struggling with a little bit. We may end up doing sort of a two-part thing. Um, I'm not 100% sure. I will, right now, what I'm planning on doing is I'm planning on basically assigning worksheets the same way that I would have in class, um, and allowing you guys to work together on them. I've set up some extra voice channels. Those voice channels will not be push to talk gated. You can use voice activity in those channels if you would like. I don't think I've set that up at this exact instant, but I will. So you can use that to talk with your classmates and ask any questions. I will also be on call from 9 a.m. to 10 a.m. What that means is that I will be sitting here either in one of these voice channels or monitoring chat, and you can reach out to me and ask me any questions you have about the stuff that you. So that way, I think we'll set it up so that I think that's the same thing we'll be doing with Tommy. If that isn't working out well, we may be changing platforms at some point. If Discord ends up not working particularly great, we might end up moving over to something like Zoom, which I'm sure Zoom and WebEx are probably the two most popular services for this sort of stuff right now. Discord just has a handful of features that I really want to be using, and it also comes with this framework of the chat stuff, which I think is really helpful. And seeing as we're all stuck at home, I'll be watching this chat pretty closely. So if you have any questions at any point, please feel free to reach out and let me know, and I will be happy to address those as soon as possible. Okay. The thing that's probably going to change the most is exams. I don't really want to be using a virtual nanny software where like there are some test proctoring softwares where they like you need to like record a video of yourself taking the test and they use that to proctor. I don't know. It's a lot and I don't really feel like it's super necessary. So what's probably going to happen is we're probably going to move to open note take home tests. Um, what this means is that obviously the amount of memorization you have to do for this class has dropped down quite a significant amount. Um, and the amount of academic honesty I'm expecting from you guys also increases a fair amount. So, for exams, and we'll talk more about this when we get closer, I do not want you to be using outsized resources that take the form of human beings. So you guys can work together in class. Please let me know if you work together on exams. Um, hey, Taylor, I think I saw your mic light up.
Yes, I think I figured it out.
Awesome, cool, good. So that's most of the people on the list. Although I feel like we've lost at least one person that was in here. Okay. Anyways, regardless, exam wise, we'll talk more about it when it comes around. Um, but it'll still take the form of a test. You'll still finish the test. Those I probably won't be doing in an online delivery method. I will probably be having, well, we'll see. I may be having you uh, basically doing write-ups for the exams. So you'll write down your answers and then you'll type them up in the form of like a write-up, just to give ourselves something that's a little bit more technologically friendly. So, like I said, that's something we will talk more about when we get into it. Um, if there are rather, does anybody have any questions about technicalities, or anything that they are trying, like technical difficulties, or any questions about the format that the class is going to take from this point forward?
So far we've missed 3 days out of this class. So are we gonna skip a portion of it, or are we gonna try
That's
to
a
cram it all in there?
Yeah, that's a really good question. So, with the expectations from sort of uh, the I guess administrative side of things is that we're still going to be hitting our or course learning outcomes. So there are some specific outcomes that we can't not hit. Like we're going to have to learn about specific things because that's what you have to learn about in order to take college algebra course. However, we'll be doing kind of a combination of those. We will be compressing some things and we will be sort of skipping some things. So I will be at some point building an updated syllabus with the information. Okay, Brooklyn. Can you try leaving and then rejoining the chat, and or leaving and then rejoining the stream? Um, so if basically we're going to still, so this unit that we're currently going into with exponents and logarithms, we will be doing it in sort of full generality. So I don't plan on cutting any content from this unit. However, the sort of the last little bit of college algebra I kind of consider to be bonus material. That's matrices and systems of linear equations, conics, um, and sequences and series. We will probably be trimming those heavily and potentially cutting them entirely. Does that answer the question, Tony?
Wrong, but yeah, that answers the question.
Okay. Hopefully, we'll get used to the push to talk thing. If it's really, really not working out, then we can talk about doing some an alternative. Did you get the video back up, Brooklyn? Okay. Keep trying, but again, this is one of the reasons why I'm recording all this stuff so I can post to YouTube, and you can go back over anything. So, um, with that out of the way, unless there are any more technicalities questions or administrative questions, I would like to jump into some math. The reason why we're all here, right? All right. So basically, in order to get into talking about exponents and logarithms, what we really need to be doing is we need to start talking about inverse functions, because that's the whole reason behind why we're going to even need to talk about logarithms in the first place. And to talk about inverse functions, we need to touch back on something that we skipped a little bit earlier on. We need to talk about the composition of functions. So to compose two functions, um, what you're essentially putting them in series. That is f of g of x takes x, and then you apply g to it to get g of x, and then you take that input and you apply f to that to get f of g of x. Basically, composing functions is when you compose two functions, you're doing one function, then doing the other function, right? So, for example, suppose one function is washing clothes. Then the other function is drying clothes. So we could do a composition where we take dirty dry clothes and then we wash them and we get clean wet clothes. Then we dry them and we get clean dry clothes. So mathematically, we might write this composition as dry and then wash clothes. So the composition of functions is not always written exactly as this. Sort of formally, definition. The composition of f and g denoted f. So we either call this f circ g of x or f of g of x. F, this circle notation I'm probably not going to use too often. It's a little bit confusing. I find that this f of g of x thing is a little bit more intuitive for most people. F of g of x is very nice because it just by PEMDAS you automatically know the order in which to do the compositions. You evaluate the inside function first because it's inside the parentheses of the outer function, right? Regardless, notation aside, is defined. Okay. So the definition I was about to write is defined as f circ g x is equal to f of g of x. So that's the definition that's used in our textbook, actually. And essentially what it's saying is that you're taking your input, initial input, and then you're applying the inside function to it first, and then you get output g of x, and then you're going to send that into f. That was weird. My Skype literally shouldn't exist, so I don't know why I got a Skype call. Yeah, it says that Skype is no longer supported, so I haven't updated. I don't know. Whatever. Anyways, apologies for that. So, composition of functions, there's actually a lot of subtle stuff that happens with regards to domain that I'm not going to worry about too entirely much. But essentially, composition of functions allows us to mash two functions together. It's something that you've actually been using over and over again. You just don't necessarily realize that you've been doing it, right? So for example, if we have f of x is equal to x plus 7 cubed, f of x is a composition of functions. For those of you who are planning on continuing onwards in the track of math through to calculus, being able to decompose functions is really important. In this case, f of x being x plus 7 cubed, essentially what happens here is that if g of x is equal to x plus 7 and h of x is equal to x cubed, then h of g of x is h of x plus 7, right? We're just plugging g of x into the h function. And what does h do? Well, it cubes things. So h of g of x is x plus 7 cubed, which is f of x. So a lot of, whenever you're doing things in a specific order, you do one thing and then another thing. Technically what you're doing is you're composing functions together. All of those polynomials we studied, you could think of them as a composition of functions, at least in their factored form. So any questions about the composition so far? So another quick example to compose two functions. Let's let f of x equal x over x minus 3, and then g of x equal 1 over x plus 2. Let's find f of g of x. So that's f of 1 over x plus 2. And when we're writing f of something, what we're really doing there is we're taking all the x's out of f and we're replacing them with that something, right? So we're going to take the x on top, and that's going to turn into a 1 over x plus 2 divided by 1 over x plus 2 minus 3. Obviously, just a quick replace does not make this a particularly interesting function. Something we can do here is we can make this a tiny bit more interesting by actually simplifying, right? So to do that, we can find the common denominator in the denominator. So we'll multiply this 3 by x plus 2 over x plus 2, which turns this into 1 over x plus 2 divided by 1 over x plus 2 minus 3x plus 6 over x plus 2. And now the denominators, we can combine that fraction, giving us 1 over x plus 2 divided by negative 3x minus 5 over x plus 2. That's the same thing as 1 over x plus 2 divided by negative 3x minus 5 over x plus 2, which is the same thing as 1 over x plus 2 times x plus 2 over negative 3x minus 5. And when we multiply through here, the x plus 2's actually cancel, and we end up with 1 over negative 3x minus 5. All right, any questions about composition? Essentially, what we need composition for is it's a tool that allows us to even talk about the next concept. So the next thing to talk about here is inverse functions. So inverse functions are basically functions that undo each other. So a process has an inverse process if it can be undone. In other words, so for example, the example I always give is tying my shoes. Normally, I would make a quick joke about how I tie my shoes every single day and then I untie them when I get home. But I haven't been leaving the house very much lately, so I don't tie my shoes very often because I'm not wearing shoes very often because I'm at home all day because of this quarantine thing. However, let's pretend that I tie my shoes every day, right? When I tie my shoes, um, we could have an inverse to this, which is untying shoes. So you start with untied shoes. You tie the shoes. You get your tied shoes. And then you untie them. And you get back exactly what you started with. And now the word tied doesn't sound like a real word anymore. So that's always nice. Some things cannot be inverted. There are some things in life that you can do that you cannot undo, right? So, for example, um, making a piece of toast. Once you take your bread, you can't untoast the bread. Um, Once you've turned bread into toast, it's toast. It might end up being cold, dry toast, but it will always be toast and it will never be anything else. So mathematically, we can apply this idea to functions. A function is invertible if there exists a different function that undoes it. Okay. The equivalent of untying your shoes, right? And it turns out that it's actually pretty easy to get something that undoes the function. The problem is getting something that's also a function that undoes the other function. And in order for this to be true, um, there is a necessary condition. And that condition is called being one to one. So, um, does anybody have any guesses what it means for a function to be one to one? It's a pretty nice bit of wording, I think, that is very straightforward. Sort of explains what it means. I've heard most of you talk. You can talk. Unless you've all walked away for a cup of coffee or something.
Is it that there's one output for each input?
So that's actually the definition of function, right? That so recall that the definition of function which is that a function is a relation such that every input yields exactly one output. So we've already got the idea of one to something, right? So, or rather, something to one. In other words, that every input can only give you exactly one output. One to one further sort of narrows that down to say that every output could have only come from one input originally. So one to one reverses this. Additionally, so a function is one to one if every output comes from a unique input. So half of one to one is already built into the definition of functions. The to one part has to be there because of the definition of function in the first place. However, the one to part is actually the part that matters. It's the part that makes a one to one function special. For what it's worth, sometimes one to one is referred to as injective, which is kind of a fancy $10 word. It is. I actually kind of like the term injective because it, from a abstract definition of functions, it sort of refers to how you're sort of injecting your image directly into whatever your destination is, right? It sort of preserves a lot of the structure. However, that's for dealing with really weird, obscure functions. So we just use one to one typically, and I will almost always refer to them as one to one. But if for some reason you're in some sort of situation and someone talks about a function being injective, what they mean is that the function is one to one. So formally, a function. So let's give a definition. F of x is one to one if for all a and b in the domain of f, if a is not equal to b, then f of a is not equal to f of b. This specific wording of the definition is the traditionally given one. It says that if one thing is not equivalent to the other thing, then their outputs must be different. In other words, if two inputs are different, then their output must also be different. Um, So, in general, this is a kind of nice way of thinking about it, but it's not a particularly useful thing to be looking at mathematically in every situation. So more pertinently, we want the contrapositive. Has anyone heard the phrase contrapositive before? Um, you may have seen it in like a logic or philosophy class at some point, if you've taken logic or philosophy. If not, that's okay. We'll do a quick aside on the contrapositive. Um, so the contrapositive to this specific statement is, so our current statement is if A is not equal to B, then f of A is not equal to f of B. I want to get rid of those not equals because they're annoying. But if I just get rid of them but keep the order of assumption the same, then it actually isn't logically true. For example, if it is raining outside, then the sidewalk is wet. If I just negate both parts of this statement, if I say if it is not raining outside, then the sidewalk is not wet. This statement is no longer true, right? The first statement is true. If it's raining outside, then the sidewalk is wet. Unless you live somewhere that has like a really nicely covered sidewalk, everywhere I've ever been, if it's raining, the sidewalk gets wet pretty quickly, right? But if it's not raining outside, then the sidewalk could still be wet, right? Um, Maybe some kids are having a water balloon fight. Maybe it just stopped raining and it's still wet from the rain. Maybe there was a giant spill of a water trailer or something, right? There are a lot of reasons why the sidewalk could be wet that isn't just rain. However, if we negate the clauses, if we say not raining and not wet, but we also reverse the order, if the sidewalk is not wet, it is not raining outside. Then we've gone back to having a true statement. And this is true for any if then statement. If the if then statement is true, the implication is true to begin with. If A, then B. Then by both reversing the order and negating both of the statements, you get a statement that is also true, right? So the logical contrapositive says that, so it takes the statement if A, let's say if P, then Q, and it turns it into if not Q, then not P. So in this case, P and Q are standing for logical propositions. Are two propositions. So in our example here, it is raining outside would be P, and the sidewalk is wet would be Q. Not P would be not raining. Not Q would be not wet. So by turning if it is raining outside, then the sidewalk is wet into if the sidewalk is not wet, then it is not raining outside. Leaves the implication of our statement intact. And to apply this to our definition of to our definition of one-to-one here. So if A is not equal to B, then f of A is not equal to f of B. This says that, so applying the contrapositive, gives us if f of A is equal to f of B, then A is equal to B. In other words, two functions are one-to-one if you can start by assuming that you get the same output on both sides. Then you have to prove that the input must have been the same. So, for example, let's show that f of x equals 3x plus 2 is one-to-one. So we start with assume f of A is equal to f of B. In other words, 3A plus 2 is equal to 3B plus 2. Well, and now we can subtract 2 from both sides, giving us that 3A is equal to 3B. And then we can divide both sides by 3, which tells us that A is equal to B. So f of x is one-to-one. It turns out being one-to-one is necessary for a function to be invertible. It's not that we can't find the inverse of a one-to-one function, of a function that's not one-to-one. It's just that if a function's not one-to-one, then its inverse isn't actually a function anymore. So a definition here, a one-to-one function f of x has an inverse function f inverse of x. So here, this exponent, when it's applied, the -1 is applied to the letter like that. This means that we're talking about an inverse function, not that it's 1 over f of x. This is a little bit annoying and leads to no end of grief when you do trigonometry. But it has a one-to-one function has an inverse function f inverse of x such that f of f inverse of x is equal to x, and f inverse of f of x is also equal to x. This goes back to that idea of the two functions undoing each other. If we take a single input, x, and then we apply the two functions one after the other, either the inverse function first and then the original function, or the original function first and then the inverse function, we get back exactly what we started with. In other words, those two functions undid each other. They collided and got rid of each other. Okay? If the function wasn't one-to-one, then you wouldn't be able to recover the information you needed, right? So, for example, f of x is x squared. This function is not one-to-one. If f of a equals f of b equals 4 and a equals 2, b equals -2, we're in trouble. We have two values that give the same output, 2 and -2. When you square them, you both get 4, right? So how would we be able to undo it? Well, we can definitely take 2 and turn it into 4, right? With f. But then f inverse has no way of knowing. F inverse can't know whether we started with 2 or -2. There's a question there, right? Like there's no decision to be made. You can't decide which one you started with. So the function doesn't have an inverse. So one thing that we'll need to do with this is determine, so example, let's let f of x equal 3x plus 2, and let's let g of x equal x minus 2 divided by 3. Determine if f and g are inverses. If I give you two functions and I ask you to find out if they're inverses, you want to use the definition of inverse function. In other words, find f of g of x and g of f of x. So f of g of x is f of x minus 2 over 3, which is 3 times x minus 2 over 3 plus 2. We can cancel the 3's. 3 times something divided by 3 is just 1 times that something. So that's x minus 2 plus 2. And then the minus 2 and the plus 2 cancel. So we just get x back. Similarly, g of f of x is g of 3x plus 2, which is g of which is 3 times, which is 3x plus 2 minus 2 divided by 3, which is 3x divided by 3, which is x. So it worked both ways. Both compositions gave us back what we started with. So f and g are inverses. A lot of you guys are going to be tempted to do this question in a slightly different way. But if I am asking you to find out if two functions are inverses of each other, I want you to always use the definition. So as a fact, inverse functions are unique. Up to simplification. In other words, if you have a function, it has exactly one inverse function. There's not a bunch of different inverses. There's only one, right? So theoretically, you could determine an inverse function by taking one of the functions, finding its inverse function, and then showing that the function you get as the inverse of one of the functions is equivalent to the other function. However, showing two functions are actually the same algebraically up to simplification is actually kind of tricky, and it's something that you have to dot a lot of I's and cross a lot of T's that we don't have time to really talk about how you dot all those I's and cross all those T's. So in general, you should expect to use the definition to find inverse functions. Okay. How do we find inverse functions? So if we're given a function that is one-to-one, how do we find the inverse of that function? Well, essentially, inverse functions take the output and return it to its input. Our first example, the one I talked about with tied shoes and untied shoes, right? We had a box full of untied shoes over here, and then a box full of tied shoes over here. Maybe F is the function of tying shoes. And that takes something from the bin on the left here in the untied shoes bin and takes it over to the bin on the right here into the tied shoes bin, right? What does the inverse function do? F inverse. Well, it takes that shoe that you just tied, it unties it, and it throws it back in the other bin, right? So the domain of F is the inputs of untied shoes, and the domain of F inverse is the outputs of F. Essentially, what we can do to find an inverse function, to find the inverse of a function, we swap the domain and range. To do that, essentially what we're doing is we're taking some f of x equals blah, 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 blah. We're going to do 4 steps. First, we're going to replace f of x with y. This is actually not a necessary step. This first step and the last step are technically not necessary, but it makes life a little bit easier when you just have one thing to worry about here. Step 2, we're going to interchange x and y. Step 3, we'll solve our new equation for y. And then step 4, we will replace y with f inverse of x. So for example, let f of x equal 2 plus 1/2 x. Let's find f inverse. Well, y, step 1, y equals 2 plus 1/2 x. Step 2, we're going to change all of our y's into x's. So x is equal to 2 plus 1/2 y. And then step 3, we'll solve for y. So we'll probably subtract 2 from both sides. X minus 2 is equal to 1/2 y. And then we'll multiply both sides by 2. So we get 2x minus 4 is equal to y. And then step 4, we'll write that as f inverse of x is equal to 2x minus 4. And we're done. We're basically just switching our domain and our range. So one more quick note about inverse functions and one-to-one functions, something I skipped a little bit when I was talking about one-to-one functions. There is a graphical test to decide if a function is one-to-one or invertible. It's called the horizontal line test. And if the vertical line test made sense to you to test if a function was actually a function or not, then the horizontal line test should also make sense to you because it's actually extremely similar. You're just replacing the vertical line with a horizontal line. The horizontal line test says that a function f of x is a one-to-one function if no horizontal line intersects the graph of f of x more than once. Okay. For example, f of x equals x. No matter where we draw our horizontal line, we're always good. But on the other hand, if we say f of x equals x squared, we're in trouble. F of x equals x squared fails the horizontal line test. So it is still a function, but not one-to-one. Okay. And that is where I will leave off for today. So a lot of these notes are coming from the outlines that are posted on D2L. So I highly encourage you, if you missed some of the notes, if I was going a little bit too fast or anything like that, then please go ahead and review these. I will also be posting this video up to YouTube as soon as I can. It'll take me a little while to upload it, but otherwise it should be up. But I will leave off there. I do have a worksheet for you guys to work on So let's go ahead and I will post that into the Discord right now. Or rather, oh no. But yeah, does anybody have any questions before I stop the stream?